Welcome everybody. Welcome back to the Bonn History and Philosophy of Physics seminar. Our speaker today is Hoyningen-Huene. Paul is one of the leading philosophers of science in Germany, was a professor at the University of Constance before becoming the founding director of the Center for Philosophy and Ethics at the University of Hanover, and then founding director of the Institute of Philosophy, and is particularly well known for his neo-Kantian interpretation of Kuhn and the leading work of which I think Kuhn said that this is the one person that understands me better than I understand myself, and worked on a wide variety of topics, including most recently on the philosophy of economics, and that's what he's going to speak about today, on the question of how do robust abstract economic models explain. Thank you very much for coming on.
Thanks a lot. I'm happy to be here again. I don't remember when I was last in Bonn, but at any rate, I'm here again. And as you rightly said, that I'm going to talk about robust abstract economic models and how they explain. That's been a long discussion in philosophy of economics over 3 decades or so. And I shall make some alternative ideas, introduce some alternative ideas. So the introduction is, in economics and in many other disciplines, you find abstract mathematical models for the explanation of real-world phenomena. And there is this contrast, you have on the one hand, you have these very abstract, counterfactual, false, in a sense, of the world models, and then you use them for explanation somehow for real-world phenomena. And the question is, how does that work exactly? How does that fit? So the example I'm using mostly, this example is the so-called checkerboard model of racial segregation, but it works for other kinds of segregation as well. And it should be called the Sarkoda-Schelling model. It's usually only called Schelling model, which is just false, because Sarkoda introduced the model. Rainer Hexelmann wrote a long article about it. So Sarkoda is completely unknown. He died unknown. Schelling became world famous, but the model is really from Sarkoda. And I give you the reference later. So this is the model. The model consists of a grid of squares and then randomly filled with white chips, black chips, and empty spaces. And you can move these things around. The dynamics of the model, that's the following: move pieces that are surrounded by only 1 or 2 pieces of the same color. So a piece is unhappy if it's surrounded only by 1 or 2 pieces of the same color. It's 3 pieces of the same color, then it's already happy. And then you move it around to the nearest empty square that is surrounded by at least 3 pieces of the same color. So this is called mild racial preferences. If you take black and white as races, could be sex, could be rankings in the military, could be whatever. So the idea is you have mild preferences. So it's not that you only move away when you're surrounded by 7, your neighbor's not of the same color, but you are happy as soon as you have at least 3 people around you, out of your 8 neighbors, right? So this is really mild racial preferences. And the dynamics will stop at some point, and the final state displays then sharp segregation in the following way, that you have here then all the black and all the white, and here the white segregated. And here's a more dramatic example. That's the following here. You see that now, you don't see the number above this. So that's the final state, right? And this begins like that. And that's this segregation phenomenon. That's a very robust phenomenon. You can start with any sort of initial condition. And you always get them after a few steps here, so I think 25 steps, you get this result. So that's the model. And the question is then, the central question of models, the transfer of results from the abstract and counterfactual model world to the real world. So the model world is clearly the world of this checkerboard with its chips and empty spaces, plus the dynamics. The question is, how is it possible that we can learn something about real-world phenomena by such a counterfactual abstract model? This is the question. And of course, economics is full of such models. And as I said, in the philosophy of economics, there's been a discussion now, more than 30 years going on, how can we understand this explanatory force of these models? So here's my outline. I start with the traditional framing of model-based explanation. And then I mentioned the explanation paradox that has been discussed for the last 10 years in economics. There's a certain paradox. And then I give you an alternative framing of the problem in 9 steps. That'll be not completely easy, and you need all what you know about logics, not all, but some of your logic and mathematics that you know, because that's unfortunately a little complicated. I tried to simplify as good as I could. So I'm at the end of my power here. And then we go from the question then I ask is how from how possibly explanations to the how actually explanation. Now, the point is the economists of philosophy of economics have introduced a terminology there I'm completely unhappy with, but this is just how they talk. Usually one would say a potential explanation. So you have a phenomenon and you have one mechanism that could explain the thing, right? It's a potential explanation. In the philosophy of economics, that's called a how possibly explanation, completely misleading. Anyway, and then the other question is, and you have several of these potential explanations, then you somehow find out, oh, that's the right one. And that is then called the how actually explanation, right? Okay. I hate the wording, but anyway, if you try out to use a private language, then you get into isolation and finally suicide, and I don't want to do that. And then because it's so complicated, I have two summaries, right? All right, so let's start. So this is the traditional framing of model-based explanations. So I'm not specifying, by the way, I'm not specifying the sort of models more. I give you this example and another example, and these are the prototypes. I have no good theory yet how to delineate exactly the realm of application of what I'm telling you. So I'm happy that I worked out the case for this model and very similar models, and that's open for discussion, and I want to learn something, how to extend that to other fields, perhaps physics. Ecology is one case, but so I'm just warning you. So I'm rather, I don't know very much how to extend that really and analyze it. So we have a model world and a real world, which is a distinction which is pretty clear in this case of the checkerboard model. One is this checkerboard with the chips there, and the other one is real phenomena in, say, American cities. And we have in the model world an explanation of the model final state by the model dynamics. Right, the model final state is segregation, black pieces, white pieces, and that is, of course, explained by the dynamics because, well, the dynamics generates it. So in the model world, you presuppose, of course, this weak racial preferences, and that generates then the final state, and that, of course, explains then the final state. So, and then we have the real world, and there is the question, how do we transfer that, to the real world? That's problematic. So Sugden, who is one of the main authors here, he's an economist by training and has published since 2000 on this question of explanation by models. And he thinks, he wrote that the first time in 2000 in his paper, he said this is an inductive step. Somehow you inductively generalize from the model world to the real world, and he reiterated that in his most recent paper from October 23. I think that's definitively false. It doesn't work at all. It can't work. This can't be an inductive step leading by generalization from the set of models to the set of the real cities. That is not an inductive step. His argument is quickly that he says, well, that's the same causality, and that's just false. Because if you run the model on a computer, the causality is really the interaction of the electrons. That's the real causality. And the causality in an American city is not running of electrons in it, it's really people moving, for whatever reasons. Anyway, I'm not going into details there. We can leave it to the discussion if you're interested. So, and then the question is, how do we transfer this explanation of the model final state in model dynamics to the real world state? And that the transfer, and this is the gap, and then Sugden discusses several possibilities, and his favorite is then to say, yes, this gap can be bridged by an inductive step. I think this is false, but that's a different story. I'm not going into detail. All right. So there is furthermore the so-called explanation paradox. And the explanation paradox was published 10 years ago by Julian Rice, one of the leading people here in philosophy of economics. And there are three premises. First of all, economic models are false of the world. Then economic models are nevertheless explanatory. And finally, only true accounts explain. And that's, of course, a paradox, is inconsistent. And then he says in his paper there, the paradox of economic modeling is genuine. I think that previous attempts to resolve it had failures. And then he says, and it's a very open sentence, perhaps thinking about how models explain in ways different from the usual paradigms is a way forward. And I can really fully agree. So one has to think, so the paradigm is the explanatory paradigms, of course. So what he says is perhaps something in our way, how we frame the problem, something must be wrong there because that paradox doesn't go away. And something must be wrong in the framing. And this is said, perhaps he says he doesn't say anything more. He just say that perhaps thinking about how models explain in ways different from the usual paradigms is a way forward. I think this may be right, and this is exactly what I'm going to do. I'm going to reframe the problem in a way such that one can understand the explanatory achievements, or potential explanatory achievements of models. But it'll be a little an arduous way, I warn you. So, okay, and I need 10 steps. I think it's only 9 steps, but that won't help you very much. It's only 10% or so. The alternative frame. So the first question now, I cut this arduous way. I cut it in 9 or 10 different helpings. And the first question that I'm asking is, what is the aim of robust models? So what do we want to do? Now, the primary aim, abstractly, is to show that a certain situation surprisingly leads to a certain results. A phenomenon that's often empirically known. So if you look at the Sarkoda-Schelling model, then it's quite clear. The phenomenon of segregation is known. Most people thought before Schelling and Sarkoda brought this up, thought, yeah, that's the result of strong racial preferences, right? They're racists, and therefore we have this segregation in the cities. So that's a known phenomenon. And then, well, what Schelling and Sarkoda said, wait a minute, surprisingly, weak racial preferences could be enough, right? And this is what they show then. So abstractly speaking, to show that a certain situation surprisingly leads to a certain result, a phenomenon that's often empirically known. And here are the examples, as I said, Sarkoda-Schelling model of racial segregation, weak racial preferences or whatever preference, as I said, many different, if you have two sorts of groups, and there can be very, very little preferences that lead to a strong segregation. You may know the phenomenon if you go to scientific conferences and you say, imagine a situation, there are then 6 tables, right? And people sit around and you are a man or a woman, whatever, and you don't know anyone. And the question is, where are you sitting? You're a woman, there are 3 women sitting there, and there's a table with 4 men, and perhaps a mixed table. Then many people, also men, would say, oops, I go to the women's table, right? Although you don't hate men, right? It's just very little. And that very little may lead to the fact then that most of the tables are full of men or full of women, right? You immediately segregation. So just to get a feeling that it's very little is needed, and this is what this model shows. All right. So the paper by Sarkoda is Journal of Mathematical Sociology, Volume 1, Issue 1, 71. And Thomas Schelling model is Journal of Mathematical Sociology, Volume 1, Issue 2, right? Both in 71. Sarkoda became completely unknown. Sarkoda already worked in the 60s with that, and Schelling became world famous and won the Nobel Prize. Very unjust story. And the other example that I'm using, and I hope some of you are familiar with that, because I struggled with that paper very much, from Richard Levins, who is a molecular geneticist. And he says he has the following, he calls it a theorem. In an uncertain environment, species will evolve broad niches and tend toward polymorphism. So this seems to be an empirical finding that in biology, and he wants to somehow understand that, Levins wants to understand that in a very famous paper from 1966, 2,500 citations, a very famous paper in which he speaks about robust theorems. You may know the slogan that the truth is the intersection of independent lies. Right? This is a wonderful statement, which you do not understand yet, perhaps, but I'm going to explain it to you, what he means. So the truth is the intersection of independent lies, and independent lies are just different models. So he combines different models, and then he somehow gets this, what he calls a theorem. All right, we'll see why he calls that a theorem. All right, so that's the aim of robust models, right? To show that a certain situation surprisingly leads to a certain result. Now, this is the primary aim. There's a secondary aim that's very important if you really look then at the work that's done in the sciences, to further specify, if necessary, the conditions under which the phenomenon arises. It may be that you have to restrict your starting point. And this also you learn in the modeling exercise that you see, oh, not all the initial conditions give the desired result, so we must restrict it somehow. And that is something which you learn. So you specify your basic hypothesis. And this is also what the models do, but I don't stress that. That's a further thing that's not part of my story. So by showing, and this is now, so to speak, summing that up, by showing that a certain situations leads to a certain result, a phenomenon, an explanation of the phenomenon is given, right? This leading to, because it develops out of that, and you say, oh, now I understand why that phenomenon has taken place. And then it's very important, the explanation is often not an how actually explanation, the real explanation of the phenomenon, but only a how possibly explanation, meaning that there are alternatives, right, of explanation. And you see that immediately that strong racial segregation may also be the result, for instance, of apartheid laws, right? If you have a city, if you look at Johannesburg in 1970 or something, you have strong segregation. Is that the result of racial preferences? Well, probably more likely the result of the apartheid laws, right? Because the blacks were not allowed to live at some places, and therefore there weren't any, right? Very simple. So the phenomenon that we are dealing with is known, but there are many different things that can produce that. So for instance, apartheid laws is one, or for instance, the economists would immediately look at uneven income and housing price distributions, right? Then you also get segregation. So if the blacks don't earn that much and the nice areas are very expensive, then you won't find many blacks there. Very simple, right? Also leads to segregation. There are many ways how segregation can occur, can arise, and therefore the explanation we get, for instance, if we get one by Sarkoda-Schelling, it's only one among many possibilities. And the next question, or the eighth question in the end, which I quickly touch only, will be how do we get from the how possibly explanation, from all these candidates for explanation, how do we get from them to the how actually explanation, what is really the cause of that particular case of segregation? All right. In physics, by the way, I mean, it took me quite some time to understand that, I got a background in physics accidentally. And in physics, we sometimes get a how actually explanation because there may be only one conceivable mechanism. So for instance, if you look at Hempel's, the old Hempel example of the bursting cooler example, you have your car and it's freezing at night, and in the morning you look and the cooler is, and then you say, yeah, how come? Well, water expands when it turns into ice, and 8% or something, and therefore, and there, I mean, strictly speaking, this is only a how possibly a potential explanation. It could have been angels, he made this thing, but this is all immediately excluded. As a physicist, you see immediately, of course, that's it, right? Sure, yeah, must be that. So, but logically speaking, this is only how possibly explanations, but usually you can, or often in physics, you can just exclude all the alternatives immediately, which is much more difficult in the social sciences, including economics. And therefore, one has to be quite aware that in the normal case, so to speak, statistically normal case, and also normatively normal cases, you only get a how possibly explanation. So a candidate for the explanation. So you can immediately not expect more from modeling, right? The best you can get is how possibly explanations. And then the next question is, okay, but I'm interested in the how actually explanation. I'll come back to that. All right. So, all right. So I said the aim is to show that a certain situation leads to a certain result. And now my question is, what's the sense of leads to? What do I exactly mean by leads to? And now you may be perhaps shocked or not, I don't know. I claim that the leads to means logical consequence. So it's the strongest possible leads to, right? And now I give you an argument why I think this is exactly what we mean when we say this leads to. Here's the example. So that would mean that the Sarkoda-Schelling model shows you that weak racial preferences necessarily lead to strong segregation out of logical necessity, right? And you say, wait a minute, that's an empirical phenomenon that can't be that strong. Well, if you look, here's my argument, in every single model calculation, so when you realize, weak racial preferences, you calculate in every instantiation of the general case, the result is calculated. And calculating means logically derived. So in every single case of that general thing, namely weak racial preferences logically imply or lead to some strong segregation, in every single case, it's logical consequence, right? So it's got to be logical consequence, can't be empirical, right? It's logical consequence. So the leads to is much, much stronger than most people assume. It's really logical consequence. I used to call it analytical connection. And then a referee told me he doesn't understand what logical connection is, what analytic connection is. I said, okay, so for my referees of the future, I write logical consequence, hoping that they understand that, which is not clear from my experiences with some of the referees. All right, so, and in the case of Richard Levins, now I've got to become a little more formal. If you haven't read the article, don't know anything about it, you won't be able to follow. Richard Levins said that robust models create robust theorems, right? He says theorems. He doesn't say empirical regularities. He says theorems. And he knew mathematics. Levins knew what theorems are, and we should take that seriously. And I'll show you how to take that seriously. Here's the example. What Levins says, this is what I said before, that evolutionary theory, if you apply evolutionary theory to an uncertain environment, then he says a logical consequence will be that species will evolve broad niches and tend toward polymorphism. That's his claim, right? So it's a logical consequence of evolutionary theory applied to uncertain environments. So models do play a role here. You don't see why. I mean, well, first of all, is that true? No idea. Anyway, so this is now logically equivalent to, this is the deduction theorem, which you certainly all remember now. This is equivalent with that evolutionary theory implies the following conditional, namely uncertain environment implies in the material sense of implication, material implication, species will evolve broad niches and tend towards polymorphism. This is just putting the stuff from the this one here, this premise here, you can put it behind the arrow, right? This is just a theorem in logics. And in other words, that means if you read that now, that of course this part here in parentheses is a theorem of evolutionary theory. And that's exactly what Levins says. It's a robust theorem. And a theorem, what is a theorem? Well, it follows logically from the premises, and the premises evolutionary theory. So what he says is that this is what he wants to have, and this is an important formula here for me because I'll show you later. So what he says is models help you somehow, we don't know see yet, to establish this logical connection. And that logical connection means in that particular case that this particular law, empirical law, is a theorem of evolutionary theory. It can be followed, logically deduced from evolutionary theory. Okay? How that works, how this logical deduction works, is a different story. But this is at least what Levins wants. And so what you see here is that when I claim it's a logical deduction, that's an issue that is shown first for the Sakota-Schelling model by the examples. And here, this is exactly what Levin wants to do. And this is why he calls these things robust theorems. Okay, if you couldn't follow here with the Levin's case, if you're not familiar with it, don't worry. Okay. Therefore, the aim is to show that a description of a certain situation logically implies the description of a certain result. Remember, I used to say it leads to, and now if we translate that into logic, I must use a description of the phenomenon because otherwise logic functions only on the level of propositions. So a description of a certain situation logically implies the description of a certain result. This is what we want to do, right? This is the aim of what we want to do here. So in other words, situation plus theory, adjunct theory leads to the phenomenon, in the sense logically implies the phenomenon. And now it's very important, although now I talk logics and it seems to be completely remote from empirical phenomena, the point is that the mechanism leading to the explanation of the phenomenon is causal. This is a causal thing. The causality sits in the premises. right? Evolutionary theory is a causal theory, which you can, under certain circumstances, apply. It's a causal thing, although you logically deduce, and you think, well, causally leading to B, something completely different from A having as a logical consequence. No, the above inference is an instantiation of the causal deductive nomological explanation scheme. Read Hempel, 1965. This is what Hempel says. What's an explanation? Deductive nomological explanation. You have premises, you have laws, antecedent conditions, and then you logically deduce a description of the phenomenon. So this is completely old-fashioned logical empiricism, what I'm doing here, right? Just bringing out the logical structure behind it. There's nothing strange, completely compatible with causality. It's nothing non-causal involved, because all the causality sits in the premises. Right? In the same case in Sakota-Schelling, you have the mechanism, namely the dynamics of Sakota-Schelling, this weak racial preference, of course, causal. I mean, that causes then the pieces to move, and that causes then the pieces to move. And once you put it on the descriptive area, descriptive level, you can say, oh, it's a logical implication, right? But the causality sits in the premises. So this is completely compatible. Although it looks logical, analytic, you know, you say, oops, what does this have to do with empirical science? Yes, it sits in the premises. And as I said, it's old stuff from the 60s, right? This is really Hempel theory of explanation. All right, which you, of course, younger people don't read anymore, probably. So now the point is now, to generate this explanatory connection, we must show the correctness of the logical inference. Right? We have the problem. Show me, why is this a logical inference? I don't see it, right? It's not obvious, right? This is what we have to do. And we have then, I described it again a little different. We have some substantive premises, description of, and they lead to the in the logical sense, to the phenomenon, right? And here the substantive premises in the Sakota-Schelling case is a mechanism, namely the weak preference dynamics, working on an initially random distribution, right? And that leads to logically implies then that the result of this dynamics is the segregation. And the same, by the way, in Levins, a theory, namely evolutionary theory, applied to specific situations. And then you get, as a logical consequence of evolutionary theory, as a theorem of evolutionary theory, this empirical law. Right? This is what you want if you can establish this logical, the deduction of the phenomenon. So this one here, you've got to establish that, right? And now I come to that. So what's the sense? So, and then the next question is, right, is why use models to establish this logical inference? I mean, why don't you say just deduce it? Come on, don't be stupid. Models to establish a logical deduction? You must be joking. No. Okay. The reason is the relevant logical inferences are opaque. You just don't see that, right? If you write down a form of evolutionary theory, it's far from obvious. That's a theorem of evolutionary theory that under certain conditions, these niches develop and the species do this and that. It's completely not obvious. You don't see that. It's opaque, right? In our examples, for instance, it was not obvious before, the Sakota-Schelling example, that weak racial preferences lead to strong segregation. People assumed you have to have strong racial preference. It's just not obvious. And when people said, if you have weak racial preferences, people would have said, yeah, they don't lead to anything, right? It remains mixed, right? That is just not obvious. And he has claimed a very strong thing. I mean, I claim it's a logical consequence, but it's not an obvious consequence. And as I said, in evolutionary theory, applied to uncertain environments, then the logical conclusion that species will develop broad niches and tend to it is just not obvious for no one. Right? You just don't see that. But the claim is very strong, and you want to establish this claim. And now my claim is, this is why you use models. Not mine, Levin saw that. Clearly, the claimed logical connection between premises and conclusion is opaque. It's far from obvious, right? And therefore, we've got to work on that somehow. And this is now scientific work, and it happens to be models. And here I give you my claim. Models are a means to tease out the sort non-obvious logical conclusions from the substantive premises. Right? And this is quite surprising. It was really, when I came to, I thought, this is really strange. But this is my story, and with the rest of the talk, I will argue this one. Right? So you have non-obvious logical consequences, and models help you to tease out these and this is, I mean, at the say, no, Hoyningen should retire finally, you know, it's crazy. It sounds crazy. Okay. I'm sorry, I can't help it, but I'm going to develop it. I'm only at step 3, so I've got 7 more steps to go. All right. So this is the idea. Models are means to tease out the sort of non-obvious logical conclusions from substantive premises. So I'm now trying to make this plausible. But first, this is only possible under one further premise. Models can only be used to tease out logical consequences from premises if the central concepts used in the logical inference are so abstract or idealized such that they are applicable both to the model world and to the real world. Okay, so this is the claim. What I'm saying, this mechanism, what models do, works only if the central concepts in the model are so abstract that they are both applicable to the model world and to the real world. Here's the example, Schelling-Sakoda. Weak racial preferences. You understand what that means for real people, and you understand, well, that's exactly what we mean when we say, okay, up to you only move away from 3 chips of the other color in your neighborhood. So you're not really hate the other color. So you see, that's an instantiation of this very abstract concept of weak racial preference. The same with strong segregation. This is applicable to a distribution of chips on this checkerboard, and it's applicable to an American city or any other city. Right? So the concepts you are using are such, they are so abstract that they are applicable to this non-realistic model world and to the real world. That's a presupposition. Otherwise, the whole thing doesn't work. And all what I'm saying is applies only for models that obey these conditions. Otherwise, we have to have a different theory. So that applies here, and it's similar in the Levin's case, but I don't go into the detail. Okay. So the desired function of models is realized in the following way. Now it's getting, unfortunately, a little complicated again, and you need some logic again. So the starting point is we formulate the claimed valid logical inference, substantive premises, logical implication to phenomenon, as a claim to general logical truth. And now you're going to remember what the definition of logical consequence is in classical logic. That's the following, namely that the following sentence, namely substantial premises and then the conditional or material implication to phenomenon, is a general logical truth. So every logical consequence can be reformulated as a logical truth. That's very important. Every logical truth containing a material implication can be reformulated as logical consequence. That's really first order. That's well, propositional logic first semester. If you've got a good logic course, you still remember it. Otherwise, I don't know what to do. Anyway, so the claim is now the logical consequence exactly the same as the general logical truth of this substantive premises arrow phenomenon. And now the next question is, we want to still, we want to argue that the logical consequence exists. So we now have reformulated, we have to argue for a conjectured general logical truth. And my next question is, how do we argue for that? Now, let's look at this a little. How to argue for conjectured general logical truths. How do we do that in general? Right? In general, we have 3 possibilities. The one possibility you are completely familiar with is very simple. It's obvious, right? Namely, semantic or logical obviousness. If you have a logical truth, for instance, all bachelors are unmarried, right? If you understand the term bachelor, which is today difficult because the word single is now replacing the word bachelor and it's not the same. Anyway, so if you understand what a bachelor is, you just know by being able to speak English in that particular case that a bachelor is by definition an unmarried man plus certain other properties, or all A are A. It's obvious, it's a logical truth. Right? You don't need an argument. Right? But there are many cases in which they are not obvious. For instance, that does not apply here because the conjectured logical truths are opaque, as I said. Right? They are not obvious. You don't see that immediately weak racial preferences lead to segregation. No, it's not obvious at all, right? So it does not apply. So the next thing is, if you do mathematics, you have a mathematical proof. Again, axioms, conditional theorem is a logical truth. That means the theorem follows from the axioms. And if that is a logical truth, well, you give a mathematical proof. So every mathematical proof for a theorem is a mathematical proof for the logical truth of axioms and conditional theorem. So we know what to do. We just construct a proof. And all of mathematics, practically all of mathematics, consists of that. Does again not apply here, because a proof for the conjecture's logical truth is not available. You can't construct a proof out of whatever, that weak racial preferences logically imply segregation. You just don't know anything. And also in the biological case, you can't do it. So what do you do then if you want to prove that? Well, now comes again something where you can declare me insane. You can inductively support a logical truth, right? Inductive, you've got to really think about it. Inductive, the guy is crazy. Okay, I show you one. Inductively support by establishing individual instances of the general logical statement, right? You have a general logical statement, and you hope it's a logical truth. And then you say, yeah, but I have no proof. I don't see. What can I do? Well, you can say, look at individual instances that support it, that confirm it. And that's then inductive. I give you examples. That's not just a creature born out of a crazy mind. This is standard practice in the sciences. And here I show you where. Inductive support for conjecture, general logical truths. This is where we move now. Inductive support for conjecture, general logical truths is not uncommon in mathematics and in science. It exists there, right? If you do mathematics, of course you use it. And if you do science, physics, for instance, you use it, and I give you concrete examples. So in mathematics, right, you have a conjectured theory, and you can't prove it yet. Well, what you do, you look at special cases, right? And you try to prove the thing for special cases, right? And then you look, how many special cases. And if you prove very many diverse, well, what do they do? Of course, they don't give you a proof. And as a mathematician, you are deeply dissatisfied, but at least you may say, wow, I'm on the right track, right? All these special cases could have been counterexamples, and they are not. Wonderful. Of course, that's not the end of mathematics, so you use it especially heuristically, right? But this is what you do. And here's a pedestrian example, right? For those who haven't followed here because they have no mathematics or no logic. Look at the following conjectured general theorem that all Euclidean triangles have an angle sum of 180 degrees. This is a theorem of Euclidean geometry. But if you don't know this theorem or you have no proof for it, what could you do? Well, showing this for particular cases provides inductive support for the conjectured general statement, right? You may either prove for particular cases that the angle sum is such and such, or you may measure them, right? And if you have no idea, real mathematicians do that. Right? You have a theorem or you have a conjecture, and then you say, yeah, is it plausible that it holds? And then you try out, right? And all sorts of things you do. And what you get in all positive cases is inductive support. This is the idea of inductive support, right? You have a general thing, and then you look at the special cases. And if the special cases agree with the general case, you don't get a proof, but you get inductive support and some plausibility. Of course, the next case can falsify you, and then you're dead with that theorem. Of course, trivial. But at least it's good to have that. And so in Euclidean geometry, you can imagine that. Now, this is mathematics, but it also holds for theoretical physics, right? And this may be surprising. And here's an example. Armin Tellung, who is not a very well-known physicist, but he was the penultimate assistant to Wolfgang Pauli, who is known to everyone in physics. And Armin Tellung wrote in a summary of a PhD thesis in theoretical physics the following. In order to get to these results, the author must make certain assumptions that appear to be reasonable, whose general validity, however, cannot be mathematically demonstrated. They should be true. So general mathematical statements, however, cannot be made as always in statistical mechanics. So this is a situation that happens in statistical mechanics all the time. You need a general mathematical theorem. You cannot prove it. So what do you do then? This is how Tellem describes it. These assumptions can only be examined by using special models, right? Which means you try to test the general assumption in special cases. That's exactly what you do. You give the more special cases you use, that amounts to a robustness analysis, and then you get inductive support for that general case. So if you ask, how does Hoyningen get to this quote and Armin Tellem? Well, Armin Tellem wrote a Gutachten about my PhD thesis. This is about my PhD thesis. Okay, so therefore, I happen to know a little about these models and their function. All right. So next step now. So we now get the idea, right? Inductive support is something. Now, how can models do that? Can they do that? How do models deliver inductive support for these general logical truths, right, that are opaque? The goal is, again, to provide inductive support for the logical truth of the following proposition, namely substantive premises, material implication to phenomena, right? How does that work? Now, if you have a model that's relevant here for what you're investigating, for instance, weak racial preferences and segregation, then the model has, of course, the substantive premises that you want to have in the real situation, right? Namely, this weak preferences plus auxiliary assumptions. So the model must make additional assumptions. In the Sakota-Schelling case, look here, it's very simple. So substantive premises are weak racial preferences working on an initially random distribution of two kinds of pieces. This is what in the abstract description is the same as in potential cities, right? In reality, namely, you have weak racial preferences and the dynamics. So the auxiliary assumptions in the Sakota-Schelling cases, the size and the form of the board, the number of pieces, the particular random initial distribution of pieces, etc., etc., etc. All the other stuff that constitutes the model. But you have these two things, and that's in the model literature quite common, that you say we have substantial premises in a model and auxiliary assumptions, and we need them, right? Now, specific auxiliary assumptions characterize the respective specific model, the particular case in question, right? So in the checkerboard case, 8 times 8, 15 black pieces, 12 white pieces, randomly distributed in the following. These are the specific auxiliary assumptions, right? And you have to start from every time you run the model, you have to start from a specific constellation. So these are the specific auxiliary assumptions. In the Euclidean triangle case, that is the substantive promise is Euclidean triangle, and the auxiliary assumptions are specific alpha and beta and the length of one side. A specific triangle, right? That's defined by 2 angles and the length of one side, then it's defined. And that's the specific, if you look at the model, it's a specific case, right, of the general theory. Now, a model run, if a model run is successful, it delivers the logical truth of a particular statement, namely the following: substantive promises conjoined with the auxiliary assumptions, the specific one logically leads to the phenomenon. Namely, you can calculate, right? In the particular case, you can calculate, and here comes the segregation, right? So it's a logical consequence. You calculate, but you have additional premises, namely these auxiliary assumptions, the specific auxiliary assumptions. Now, each such two particular statements provides inductive support for the logical truth of the general statement, namely substantial premises imply the phenomenon. In other words, the logical truth of that is the validity of the logical conclusion, namely from the substantial premises to the phenomenon. This is what we want, right? We want to have the logical implication of the phenomenon from the premises, the substantial premises. And every model calculations gives you an instance of that, just giving inductive support to your general state, right? And this is what I'm claiming here. The robustness of a model now means, and this is now of utmost importance, the robustness means in this literature, robustness means different things to different people. In this literature, it means that the logical truth of substantial premises plus auxiliary assumptions, specific ones, imply the phenomenon, holds for many different auxiliary assumptions. So you can play around with the auxiliary assumptions. So in the Schelling-Sarkoda case, it doesn't have to be 8 times 8, can be 10 by 10, 100 by 100, 125 by 125. You may build rivers in between and whatnot, right? So you can play around, and the point is the robustness of the model says you can play around with these auxiliary assumptions. The conclusion is always the same, right? Suggesting that the conclusion does not depend on the specific auxiliary assumptions. That's the idea. And that's the idea of robustness, right? The result is independent of these, largely independent of these auxiliary assumptions. And that then delivers strong inductive support for the logical truth of the general proposition. This is what we want, right? We want to show that the phenomenon is a logical consequence of this substantive premises. That's the whole idea of modeling, right? So I don't know whether you follow anyway. So by the way, this is also important here to see that, to have the mathematics clear, an ideally completed robustness analysis would result in a proof, in a mathematical proof of the general proposition. Why? Because it shows that no counterexamples exist, right? This is the connection. So if you have robustness, and in the limit, then robustness is, so to speak, an incomplete proof. It's a proof as soon as you can calculate, of course, infinitely many cases, and you can't, but this is just the connection between proof and robustness analysis. All right. So, step 7. Now, how does the explanation finally work, given this idea here that the models inductively support a logical truth or the validity of a logical consequence? How does that work? Now, that's the following. A robust model delivers strong inductive support of the logical truth of the general proposition, substantive premises imply phenomena, right? Material implication. That should be logical truth, because this is equivalent with substantive premises logically imply the phenomena, right? I'm sorry, you have to use this definition, otherwise you don't get the inductive support machinery not running. Okay. So we have then strong support for this logical implication. And the point is now that the description of the substantive premises and of the phenomenon apply equally to the model world and to the real world, right? This is the point why I said that the terms in the models must be so abstract that they both apply to the model world and to the real world. Weak racial preferences is understandable in the model world and in the real world, as is segregation, right? It applies both to this checkerboard and it applies to the real world. That is the bridge there. It's necessary to have this bridge. So this is, of course, important here, because then we get a causal, deductive, nomological explanation for the phenomena, both in the model world and in the real world at the same time, right? This is one and the same step, right? We get something very conservative, a Hempelian deductive nomological causal explanation. No one cares about that anymore, right? But this is what models do, and therefore it's worthwhile to know the Hempel story, because the Hempel story is, of course, incomplete and many things are missing, but you get exactly that same skeleton in the model explanation. And this was, for me, completely surprising. I had not expected that at all. The transfer problem, model world to real world, has disappeared, funnily enough. I mean, that almost never happens, that a problem disappears. Well, you get, of course, another problem instead. So it has disappeared because the connection between substantive premises and phenomenon is logical and not empirical. If it was empirical, then you cannot transfer it to foreign cases that are very different, right? Because empirical laws don't translate there. But if it's logical, it does. So if you underestimate the strength of the connection between substantive premises and phenomenon, you think, oh, wow, we have a transfer problem. But once you see that it's a logical connection, the transfer problem simply disappears, right? It's not there, all right? So how does the explanation work? Well, I show you. You have robust model results. The robust model results inductively support a conjectured, non-obvious logical truth, right? The logical truth that embodies the logical consequence relation, right? And it's conjectured because you have no proof for it. It's non-obvious, therefore you need something else, and it's a logical truth. And this non-obvious logical truth can be immediately applied both to the model world. You get a how possibly explanation in the model world, and you get for the real world also the how possibly explanation. If you understand the Sarkoda Schelling model, you know, oh, in any time I have here in the model world at the end segregation, a possible explanation is weak racial preferences, right? And you get at the same time, if you have any American city and you have segregation, a possible explanation is weak racial preferences. And you get that in one single move, right? Because the connection between the description of the phenomenon and of the consequence is logical and not empirical, right? So this is vitally important to see that. How am I doing this time? 2 more hours? Okay, good. All right. So the difference between the traditional framing and the new framing is in the traditional framing, you have a gap between model explanations and real-world explanations that has to be bridged and is cursed with the explanation paradox. And then you say, well, how should that be? And therefore, Rice says, well, we need something else. We need a different framing. And this gap is now replaced by a new gap. Of course, you don't get rid of all the gaps at the same time. Yeah, there's a new gap, and the gap is now between instances of a non-obvious logical truth, namely the single model calculations, and the general logical truth itself. So we've got a gap here, so we can only calculate single instances, and in robust models, you get the feeling that, oh, they strongly inductively support the general logical truth. So we have another problem here. It's also a question of induction, but a very different sort of induction, namely an induction that supports a non-obvious conjectured logical truth. So why does the explanation paradox disappear? Step 8. If you don't worry about the explanation paradox, I do it a little quickly. Again, economic models are false. Economic models are nevertheless explanatory, and only true accounts explain. Indeed, instead, economic models instantiate general, non-obvious logical truths, thereby inductively supporting that. So it's a very completely different logic. And the paradox, explanatory paradox, does not appear. These non-obvious logical truths embody the explanations in the same way as in Hempel's DN explanation, the logical truth explanans implies material implication explanandum. That's also a logical truth in Hempel. So it's all old stuff that I'm presenting here. You've got to see how it's there in the models. This is exactly the same. Remember, you may remember, probably it's not even taught anymore, the Hempel theory of explanation, right? You have the laws and you have the antecedent conditions, and they logically imply the explanandum. Yes, that's exactly this one. I don't do anything else. I'm only saying, because we can't establish, unfortunately, so easily the logical truth here of explanans logically implies explanandum, because that's the same as the logical truth of this one, of this piece here. We cannot establish it as simply. But that's the idea of that models can do that, right? So models help you to generate the Hempelian scheme of causal explanation, because the causality sits also all in the explanans, as in the Hempel case. All right. So here's a criticism. How am I doing in time? Have I 5 more minutes?
5 minutes, yeah.
5 more, okay. Yeah, so there has been a discussion that Saxton, who discusses that, says as a criticism that an understanding of modeling as conceptual exploration and nothing else is not convincing. Conceptual exploration investigates the internal properties of models without considering the relationship between the world and the model and the real world. And this is quite plausible, but if you look at my account, then model explorations may produce inductive arguments for non-obvious logical truths. And these logical truths makes explicit logical consequences of certain assumptions. And due to their non-obviousness, these logical relations provide how possibly explanations that are immediately applicable not only to the model world, but also to the real world, wherever the assumptions hold. So Saxton overlooks a certain possibility because people have not realized that the connection is so strong. It's a logical implication, and that changes the picture. Now, the next question would be how, from how possibly explanation to the how actually explanation. And there I give you a very simplified story. In general, it's so if you have a number of how possibly explanations, then you've got to eliminate all but one. assuming that the real explanation, the actual explanation, is part of your set. That's again, it's trivial, right? It's not so trivial because this assumption is a simplification, because the real explanation could be a mixture of different mechanisms altogether. But anyway, so you've got to eliminate them, it's tricky because even it's so go down here, unfortunately, we come line by line. If you have a city with measured weak racial preferences and racial segregation, it's not clear that therefore the weak racial preferences are the explanation, because the city could be under apartheid law, or it could be other factors, and then you have other factors that produces and not the racial difference. So it's more complicated, but in general, the strategy seems to be clear, and this is not the main part of my talk. So summary one is the following. We are in a model world, and in a model world, we have a final state, and abstractly is that identical with a real world state, right? So we think of segregation of pieces on the checkerboard, or we think of racial segregation at an American city, or at the initial day of the conference, more women sitting together and more men sitting together than mixed tables, right? This is the phenomenon. So this is the model final state, and then we invent a model such that the model develops into that final state, right? This is fine. If it does that, then you must do robustness analysis, right? Is that model robust? Right? Can we vary the inessential model parameters and still get the result? So if that's not the case, then away with the model, get a new model that's hopefully robust. So let's see, we have positive, here is negative, then it's eliminated. Let's see, robustness analysis, yes. Then the model gets inductive support. What does it inductively support? A logical truth, right? This non-obvious logical truth. That logical truth can be directly applied to how possibly here you see, can't read that. How possibly real-world explanation, right? This logical truth, as I said, is a logical consequence, premises to conclusion, and that can be applied to the real world. But this alone doesn't help us because we have only one model and there are the other models. So what we have to do is we have to calculate more models. So not only this one, but then we make then robustness analysis, for instance, housing prices and with apartheid laws and with strong racial preferences and blah, blah, blah. And then we get several logical truths, all potential explanations, right? How possibly explanations, how the economists say. And then they can all directly apply to the real world. So if you have the phenomenon of segregation, yeah, it can have various causes, and you don't know which one. And again, then what you have to do is you have to eliminate, hopefully all of them, apart from one, and only one is left. And this is then you have actually a real-world explanation for the phenomenon. So this is the logic of the whole thing, how the research process simplified happens. So this is summary one. And here is summary two. The function of robust abstract models is to tease out non-obvious logical consequences of mechanisms. This is the more general expression that's also used by Schelling and Sarkoda. So weak racial preference is a mechanism, right, that sets things in motion, of mechanisms, Sarkoda Schelling dynamics, or theories, for instance, evolutionary theory, in the case of Levins, that cannot be directly inferred from that, right? So we have the power of these mechanisms or the theories, and we cannot see how this power really develops, but we can if we use models, right? Robust models. They do that trick. For this teasing out to work, models need auxiliary assumptions not contained in the substantial premises. And they are, of course, awful because you don't want to have them. They are irrelevant for a problem in case, right? In order to neutralize the influence of these auxiliary assumptions, robustness analysis is necessary, which cancels their influence on the results. And this is why Levin says the truth is the intersection of independent lies. So every assumption in every model is false. So it's a lie about reality. But once you take the intersection, namely where they agree, where these auxiliary assumptions don't play a role, which is done by robustness analysis in this sense, Then you get the theorems out of evolutionary theory, namely a certain empirical law as a consequence of evolutionary theory. And this is what models do. Thank you very much.